Alright, welcome back to another video for elementary statistics. We have a monster of a chapter up ahead of us, so I hope you have your note-taking utensils and your calculators and anything ready, because we're gonna start ramping up the stuff for this video, okay? We'll be working with describing and comparing data, specifically three main topics: the measures of center, measures of variation, and measures of relative standing. And if you recall from last video, we got a surprise visit from boxplots. So let's see what they have to offer once more. So without further ado, let's go. Before we get into the measures of center, I do want to talk about resistance. A statistic is resistant if the presence of extreme values doesn't cause it to change very much. Some books also call resistance robustness, so you can see either of those two or both. And extreme values are typically called outliers, so those are the more common term for it. Some statistics are more robust than others, and later on, once we get to these statistics, I'll tell you which ones are resistant and which ones are not. So yeah, let's get to it. The mean. The first time we see the mean, it's probably in elementary school. That's when it's first introduced to us, and it's kind of a neat little math experiment that we do back then. More officially called is it's called the arithmetic mean, or just the mean is also fine. So if you recall, we find this mean by adding all the data values together and then dividing by how many data values we had. There's a special rounding rule for the mean, and is that we round to one more decimal place than is present in the original data. And the mean is not resistant, since it takes into consideration every single data value. If some of them are outliers, then it's gonna shift the mean one way or the other. It doesn't necessarily mean it's bad. The mean is actually one of the most useful measures of center out there. It's just that's the way it is. And underneath we got some formulas there. We won't be doing much by hand because it takes too long. And also we got some technology that can help us find this very quickly. And the picture here, I really like it because the mean is basically the balance point, or the fulcrum if you want to be fancy about it, if you take physics and whatnot. It's that balancing point between all the data values. So I really like this picture. And make a note of the mean. The mean will be seen throughout the rest of the course. It's going to be super important. I do want to try an example of finding a mean given a data set, but I'm saving it for later. You'll see why. Another kind of mean we can find is from a frequency table. You recall from last video, frequency table is just a organized way of presenting data, and we can find the mean from it. First thing we gotta do though is find the class midpoints, which we call X, and F are the class frequencies. Now, the mean from a frequency table is an approximation, hence that picture right there. It's not gonna give us the exact mean from that original data set, so just keep that in mind. Alright, so here's our neat little frequency table from the last video. Now let's say that we wanted to find the mean of this table. First thing we gotta do is find the class midpoints. Now how do we do that? We need to get both the endpoints of the class, add them together, and then divide by 2. For example, 6 plus 0 divided by 2 will give us a 3. 13 plus a 7 divided by a 2 will give us a 10. 20 plus 14 divided by 2 is 17. So we do this over and over until we have all the class midpoints. Now with these two last columns here, those are the ones we're going to use to find the frequency table. And there's a neat way to do this with the calculator and with StatDisk. So let me show you the calculator way first. I have the calculator open over here. As you may recall, you get to a list, we go to Stat, and we can go to Edit. We're finding the mean of a frequency table, right? So let's input the class min points and the frequencies into two different lists. I'll use list 2 for the class midpoint. So I'll put in a 3, 10, 17, 24, 31, 38, 45. Nice. And always double check the list once you finish inputting it. So it seems that I got all the values there. Nice. And now the frequencies. 3, 3, 10, 11, 8, 3, and 2. Alright. Double check. Yeah, it's fine. Okay. So now let's find the mean of this guy. To do that, go back to the main calculator window. We're going to go to Stat. And now we'll choose Calc. That's going to allow us to find a lot of cool stuff. So here we've got list, frequency list. Our regular list here will be the class midpoints, which we put in list 2. Our frequency list, that's what we put in list 3. So we go second and then 3, because it's got the list 3 right there. And the last thing we need to do is press calculate. And that's going to find the mean for us in an instant, which is really cool. So the mean, if you may recall, is X bar. And according to the rounding rule, we round to one more decimal place than the original data. So our very original data were all whole numbers. So that means we just round to one decimal place. In this case, 23.1 would be the mean for this frequency table. Just like that. Really neat, huh? Now, how about we try this in StatDisk? Let's go. Alright, everyone. So, I have a bit of bad news for StatDisk. I tried to find a way for it to calculate the mean of a frequency table, and I just was not able to find the function or anywhere. So, I just did the good old-fashioned search it up on the internet. I hit up DuckDuckGo and not Google, because they're creepy and they keep track of everything you search for. And I searched for frequency mean or frequency table mean calculator. And the one that I really liked is this one here. It works. It's a little weird to input the data here into this text box, but I mean, whatever. This is as good as it's gonna get. So to use this online tool, we need to input first our midpoints, right? That was the first column in our frequency table. And the way it wants it written is to write, for example, the first item, and then a comma, and then a space. So 10, comma, space, 17, and then we got a 24, and we got a 31, 38, and 45. Double check that I got all the values there. 3, 10, 17, 24, 31, 38, 45. Nice. Now to input the frequencies, we first need to put an F with the colon, and then we go ahead. So 3, another 3, 10, 11, 8, 3, 2. Once we got all that going, then we just hit calculate. If we scroll down, oh cool, it does a whole bunch of other stuff as well. But what we're really interested in is right here. the mean. And as you can see, it's the exact same value as the calculator. Got a 23.1 if we round using the special rule. So there we go. So you can use this calculator by hackmath.net. Another kind of mean we can find is what we call a weighted mean. Data values are x, and every x value has an assigned weight, which we call w. A very common way of finding a weighted mean is with a report card. Ever wondered how they calculate your GPA? Well, we'll learn that now, and we can actually do it. So, after their first semester, Agatha got these grades on her respective classes. A B in English, a C in history, an A in math. Good job, Agatha, you're amazing. A B in art, and a C in psychology. So what's her GPA for that semester? We need two things before we can do this. We need to find the college grading scale. Most colleges use this grading scale here. So A is equal to 4 grade points, B is 3, C is 2, D is a 1, and F is a 0. Some schools may have different grading systems, so just find whatever grading system your school has. And then we also need to find how many units or credits each respective course has. So English has 4 units, history is a 3, math is a 5, art is a 3, and psychology is also a 3. So now, let's organize this a bit with a table. We got the college courses there on the left, the course letter grades that Agatha got, and the course units. What we need to do here is switch the letter grades to the grade points. So how much points is each letter grade worth? And if you recall, B was a 3, C is a 2, A is a 4, B is a 3, and C is a 2. And once again, these last 2 columns will be the ones that we'll use to find the weighted mean. Let's go over to our lists and then edit. And now here we have the frequency table, the class midpoints and the frequencies. I want to use list 2 and 3, but I don't want to delete each of these values individually. So a neat little shortcut you can do, just go up to the list's name, so L2, and then just hit clear, and then just hit enter, and bam, the whole list is gone. That's much quicker. Clear, and then enter, bam. And now we're free to input some new values. So we got a 3, got a 2, 4, 3, 2. Nice. Double check. Okay. Now the units. It's a 4, 3, 5, 3, 3. Bam. Nice. Now to find the weighted mean, it's the exact same process as finding a mean from a frequency table. Just go over to stat, move over to the calc window, one more stats, and because we did that mean of the frequency table before, we have list 2 and list 3 already there. If they're not there, just input them second, and then list 2 is over here, so press a 2, second, 3 for list 3. So yeah, so then we calculate and we find the weighted mean, which is right up there, x bar. So that's a 2.94444. Once more, I believe the weighted mean also follows the same rule as rounding to one more decimal place. However, for GPAs, it's a common practice to round to 2 decimal places. So Agatha's GPA for that semester was a 2.94. Man, those C's really take a toll on your grades, huh? Yep. But there we go. Oh, right. And since the weighted mean is the exact same process as finding the mean of a frequency table, StatDisk will also not be able to help us there. But that's why we got hackmath.net to the rescue. So once again, we'll be using this online calculator to help with this problem. So once more, we input the course weights, the grade points, separated by commas in the space. 4, 3, 2. And then we put in the weights. We still need to put in the F because that's the way that the website here wants it written. And then we put in the weights. 4, 3, 5. Oops, forgot a comma. 3 and 3. So once we got that there, we calculate, scroll down a bit, and look at that. Got the mean. And since it's a GPA, we rounded to 2 decimal places as well. So that'd be just a 2.94. Bam. And there we go. That's that, finding the weighted mean. So, yeah. All right. Moving right along. The median is our next measure of center. And this guy is a really cool guy. The median is the exact middle value of a sorted data set. And whenever we say sorted, we mean that it's the data values are organized from least to greatest or greatest to least. The more common way is least to greatest, so that's what we'll stick to throughout this course and video. Some ways the median can be written, or some symbols to refer to the median, is just med. Also, you may see Q2 or P50. And some use X tilde. It's not really common. It's kind of like a hipster symbol. So if you want to be a hipster, you can use that last one there. But the first 3 are the more common ones. The same rounding rule applies here. Round to 1 more decimal place than in the original data. And the median is resistant, since it kind of doesn't care about the outermost extreme values. It just kind of ignores them. And yeah, that results in it being very resistant. I do want to try an example. I do have an example for finding a median, but I'm saving it for later. You'll see why. Our next measure of center is the mode. The mode is, in essence, the value that occurs the most. Something really neat about the mode is that it could also be found if you have categorical data. The mean and the median is strictly only for numerical data, but the mode, you can use it if you got some categorical stuff. A data set can have 1 mode, 2 or more, or absolutely no modes at all. And it is the most resistant measure of center out there. Since it doesn't care at all about any other data value except the most popular one, that's why this makes it the most resistant. It's not one of the more commonly used ones. You may see it, but it's not too great of a measure of center. And speaking of not too great of a measure of center, we got the mid-range. It's a value midway between the max and min from the original data set. The formula is pretty self-explanatory. You add the maximum plus a minimum and divide by 2. We have the same rounding rule, round to 1 more decimal place than the original data. And it's not resistant. And this kind of makes sense because it's using the 2 most extreme values out there. So if those values are extremely extreme, if they're really extreme outliers, then it's gonna shift the mid-range up or down. And the reason for this picture here is that it's not useful. Yeah, the mid-range is not commonly used. It's just not. No. I mean, if you're in a hurry, if you need to go, if you're late for a doctor's appointment and you really need to find the measure of center for a specific data set, then yeah, go ahead and use the mid-range. But other than that, it's kind of a bad one. So yeah, we'll not use it at all. Our next topic are measures of variation. So let's see what different kinds of measures we got for variation. The very first one here is the range. The range is the difference between the maximum data value and the minimum. And its formula is also very self-explanatory. You just get the max and subtract the min. The same rounding rule applies, one more decimal place than original data. And it's not resistant, similar to the mid-range. It's using the most extreme values of the data set, so if there are some really heavy outliers out there in this data set, the range is going to be thrown all over the place. Moving on is the standard deviation. So this guy right here is a measure of how much data values deviate away from the mean. So the standard deviation and the mean are really closely related. Same rounding rule as before, and the standard deviation is also not resistant. At the bottom here we have many different formulas. If you can see there, the population standard deviation and sample standard deviation formulas look kind of similar. The only difference is the denominator there. For the population, it's a capital N, so the population size. And in the sample standard deviation, it's N minus 1, so sample size minus 1. So watch out for that difference there. The sample standard deviation is the one we'll be using the most. And there's this third one that is actually a shortcut formula. You may be wondering how in the world it's a shortcut, because it's got a lot more things going on. If you can see in the first two formulas, we are using the mean. It's inside those parentheses, so the x minus x bar. So we first find the mean, and then we find the standard deviation. That third formula allows us to skip finding the mean, and we just go straight to finding the standard deviation. So that's why it's quote-unquote a shortcut. Software and calculators find the standard deviation using that third formula. That's how they're embedded into the programming. So that's a fun fact of today. Standard deviation is also massively important. We will be seeing it a lot, so make a note of this little guy here. I also have a practice problem for finding a standard deviation, but once again, I'm saving it for later. There is a rule of thumb for finding the standard deviation. It's approximately the range divided by 4. And big emphasis on approximately. Once again, if you're in a hurry because you're late to class and you really need to find a standard deviation of some sample, then yes, you can go ahead and use this rule of thumb. But yeah. There's another part that's kind of interesting for this range rule of thumb. It has to do with significant values, also known as usual values. So the vast majority of sample values, about 95%, lie within 2 standard deviations of the mean. So in order to visualize this a little better, I have a little diagram here. So we have the mean right there in the middle. And as we recall, it's a measure of center, so yeah, it's got to be in the center. If we add 2 standard deviations to the mean and subtract 2 standard deviations from the mean, all this in the middle will be values that we consider not significant or usual. But anything lower or greater than this, we can call significantly low or significantly high, as well as unusually low or unusually high. So that's what this rule of thumb is telling us. It's a little bit of useful information. There is another rule that I will go over in this video, and then we'll go a little more into depth with this 95% and stuff like that. So it'll be cool, I promise. Next up is the variance. So the variance is measure of variation equal to the square of the standard deviation. And that's pretty much all that it is, just the standard deviation squared. In fact, if you look at the formulas at the bottom, they look very familiar to the standard deviation ones, except we just got rid of the radicals. So yeah, same rounding rule, just one more decimal place than the original data, and it's also not resistant. And that's pretty much all there is for this guy. I do have a practice problem for the variance, but one more time, saving that for the end. Here's the rule that I was talking about, the empirical rule. If we have a data set that is normally distributed, then the following apply. And if you recall from the last video, normally distributed means that it follows this pattern. Starts off low, and then it starts to steep up and up and up. Then it kind of peaks. Then it just drops low, and then it flattens out over there on the right side. So, if we have this kind of distribution, then about 68% of all data fall within one standard deviation of the mean. Then about 95% of data fall within 2 standard deviations from the mean. And about 99.7% of data fall within 3 standard deviations. So now what in the world does this all mean? I got this next diagram. I really like how this slide came out. So once again, this is our normal shape. It's kind of like a bell shape curve, as we call it. The empirical rule states that if we drop 1 standard deviation down and go up 1 standard deviation, then 68% of all data will be there in that blue chunk. Now, the mean right there is in the middle. So if we were to just kind of slice up, because the normal distribution is symmetric, then we have exactly the same shape on one side to in the other. So that means that this 68% will also be sliced in half, meaning that we have 34% in both of those blue chunks. But we can go a little further. Empirical rule states that within 2 standard deviations, so we go down 2 standard deviations and we go up 2 standard deviations, that accounts for 95% of the data. And if we were to subtract the 68%, we end up with 27% remaining. Since we have 2 yellow chunks here, we divide 27% by 2, and that gives us 13.5% in each of those yellow chunks. Well, that's kind of neat. But we can go even further. This rule also states that if we go down 3 standard deviations and above 3 standard deviations, that accounts for about 99.7% of all data. If we were to subtract the 95 and everything in between, we end up with a 4.7%. And because we have 2 green chunks, we divide that by 2, and we get a 2.35% in each of those green sectors there. But we can go even further. 100% of all data is going to fall within the entire bell shaped curve, right? If we were to subtract the 99.7%, then we end up with the 0.3%. And since we have 2 red sections there, we divide by 2 and we end up with a 0.15% in each of those red little parts. So this is the ultimate slide for the empirical rule. This slide took me like an hour or more to finish, so I'm really proud of how it came out. So please take a picture of this and print it out and then put it in a picture frame and hang it on your wall or whatever. So yeah. Moving on. Chebyshevs Theorem. So, hello, Mr. Chebyshev. This theorem it's a similar concept to the empirical rule. We're trying to find how much data lies within a certain amount of standard deviations. The empirical rule is an approximation, whereas the Chebyshevs theorem is absolutely correct. It's exact. Now the problem is that we don't work with Chebyshevs theorem. In fact, we're never gonna see Chebyshevs theorem ever again in any of the other videos. It's just not gonna be there. So I'm sorry, Mr. Chebyshev, but we have to move on. Another topic that is also commonly skipped between professors: the coefficient of variation, also known as just CV. It describes the standard deviation relative to the mean. This one has a special rounding rule of just 1 decimal place of a percent. So it has to be in a percent and then you round to 1 decimal place. You got the formulas down there for a population and a sample one. Same thing as Chebyshev. We're probably not going to see it ever again, so we won't be dedicating too much time to it. But yeah. So our last topic for today will be measures of relative standing and, drum roll please, box plots make a surprise reappearance, so let's see what they have to offer. Alright. First measure of relative standing is a Z-score, sometimes also referred to as a standard score or a standardized value. It's the number of standard deviations that a given value x is above or below the mean. This one has a distinct rounding rule. We typically round to 2 decimal places. And there we have the formulas for those two. These scores are very important, but I do want to wait and use them later on. Some professors do start working them with the Z-scores, chapter 3. I want to wait because there are some other cool things that we can do with Z-scores that we do later on. So yeah, I think it's best to wait on this, but at least now you know the formulas and that we will be seeing them later on. Percentiles. Oh boy, percentiles. These are measures of location. They divide a data set into 100 groups, and there's about 1% of all data values in each group. The symbols we use to refer to a percentile are P1, P2, and all the way up to P99. If we take a brief look at the picture, we got a couple of people there organized from shortest to tallest. And that blue lady there, she is in the 80th percentile. In other words, she separates the shortest 80% of people in that data set from the tallest 20% of people in that data set. So that's what percentiles do. They kind of divide certain sections up depending on how we want to chop the group. And underneath here, we have one formula. This is to go from some data value x to its actual percentile. So the percentile formula here is percentile of x is equal to the number of values less than x divided by the total number of values and multiplied by 100. And the rule for this specific formula is to round to the nearest whole number. Now, there is no consensus on how to find a percentile. Your book may have a completely different method for finding these, so just be wary of that. I'll be using this method here, and I will show you how to do it. Now, percentiles, we will be seeing them later on. We won't be actually finding them using this method. We'll be finding them using another method. But finding percentiles is so weird. It took me a really long time to wrap my head around this idea and actually find one. So that's why I do want to show an example here, step by step, because it's just so awkward. You'll see in a moment. So we have our good old data values from before. Remember, these is from last video? Yeah. So let's say that the instructions say find the percentile for the data value of 24. The first thing we need to do is to sort our data. And as I mentioned before, sorting our data means arranging from least to greatest. So how about we do that? There we go. It's a nice organized table there. So these are all our data values from least to greatest. Now we need to find the percentile for 24, right? So we got this formula here. The percentile of 24 is equal to the number of values less than 24 divided by total number of values times 100. So let's locate 24 in this chart, and it's right there. Now what we need to do is count how many values are below 24. So that's 1, 2, 3, 4, 5, 6, 7. And then we got 8 up there. 7 plus 8, that's a 15. Plus another 8. All of that equals 23. So we have 23 values that are less than 24. And we have a total of 40 values. And we're multiplying that by 100. So when doing all that, we get 57.5. As the rounding rule states, we round to the nearest whole number. So the 5 rounds the 7 up to an 8. So we get a 58. So a survival length of 24 months is in the 58th percentile. That's exactly what we found. So yeah. Now how about if we wanted to go the other way around, and we start at a percentile and we want to find the data value? Then it's a totally different process, and it's also kind of weird. So this is what we do. From a percentile to a data value. To find the kth percentile, find L, which stands for locator. L will not be the final answer. It's going to help us find the final answer. L is K, K being the percentile we have, divided by 100 times N, where N is the sample size. So how many data values do we have? Once we find L, we need to use the following flowchart. And flowcharts are cool. So we find L and we ask ourselves, is L a whole number? If it is, then the kth percentile will be the Lth value in our data set plus the next data value in the data set. And obviously ordered from least to greatest, divided by 2. Now, if it's not a whole number, then we round L up to the next whole number, and the kth percentile will be the Lth value. So, it sounds completely out of whack, right? Yes. So let's actually work this problem out. It's the exact same data set, the survival lengths from the last video. Now they want us to find the 58th percentile, or P58. First thing we got to do is find L using our handy dandy formula. So L is K divided by 100 times N. K is the percentile that we have, so it's going to be 58, and N is our sample size, which is 40. So we plug those values in, multiply, we divide, all that fun stuff. We get a 23.32. Now is where we use a flowchart. Is L a whole number? And we can clearly see that it's not. It's 23.2. It's got a decimal. So then the flowchart says to round L up to the next whole number. And then the kth percentile would be the Lth value. So in our problem, we round 23 up. No matter what the decimal point is, we just round up to the next whole number. So that's a 24. So then the 58th percentile will be the 24th data value in our sorted data set. And as I mentioned, L is not the final answer. It helps us find the final answer. So let's sort our data once more. Bam. There we go. So just copying a few values from before. L is 24. And that tells us that the 58th percentile will be the 24th data value. So then we go to our data set and just count 24 spaces, starting with the lowest and going up to the largest. And we'll see where the 24th data value is. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So the 58th percentile is 24. Now you may quickly notice here, hey, you said L is not the final answer, and it's 24, and the final answer is 24. That was a massive coincidence. I did not plan that out. In fact, I should have probably used a different example, but it's too late for that now. So it's just a coincidence. It's not always going to happen. As I said, L stands for locator. It helps us locate where our data value is. So 24 means the 24th data value in the sorted data set. So yeah, watch out for that. Moving right along, quartiles. They're similar to percentiles, except now they're cutting the groups such that they have about 25% within each group. 25% of data values. The symbols we use to denote them are Q1, Q2, and Q3. And one of the most common things we can find with quartiles is the interquartile range, or IQR. It's just Q3 minus Q1. I will show you how to find quartiles at the end. I'm saving all this good stuff for later. Alright, now we got the 5-number summary. I briefly mentioned this in the last video. It consists of the minimum, Q1, the median, Q3, and the maximum. And if you recall, the median is also sometimes called Q2, or the second quartile, or P50, the 50th percentile. And I will also show you how to find this at the end. Be patient with me, please. Hey, we got the box plots. They're finally here. So, as a brief recap, it's just a graph of the 5-number summary. But we have a modified box plot as well. That is just a regular box plot that also shows outliers, those extreme values that we mentioned way back when. So, an outlier by definition is a data value greater than Q3 by 1.5 times the IQR or more. Or if it's lower than Q1 by 1.5 times the IQR or more. So in the picture there, we have a box plot, but those two dots are way above the third quartile by that amount, 1.5 times the IQR. So yeah, that's the box plots. Now, are you ready for the ultimate review? We have our good old data set from before. Now we're gonna find and do a lot of cool stuff. How about we find the mean, standard deviation, variance, the 5-number summary, and we construct a modified box plot for this data set. You may be saying that's way too much work, and I'm already too tired after doing all this stat stuff for today. Don't worry, the calculator can do all of this for us, and we're just gonna sit and relax. How's that sound? Alright, let me show you how to do this on the calculator. Now, to find all the values that I mentioned, the mean, the standard deviation, and all that jazz, we've actually already been using that special calculator command. It's one_var_stats. We're gonna input list1 into list. And since we don't have any frequencies at all, we're not working with them, we're just gonna leave the frequency list blank. So we'll just delete. And now when we press calculate, we'll see a lot of cool stuff. You ready? Bam. Okay. So here is our mean, x bar. If you recall from the mean from a frequency table, we got a different value. And that's because the mean of a frequency table is an approximation. This is the actual mean for this data set. But the mean is not the only thing we have. We go a bit down, we got the standard deviation, Sx, which is all the way here. The sigma x would be the population, standard deviation. In this case, we have a sample, so that's why we'll use the Sx. And if we were to use the appropriate rounding rules, our original data has no decimal places. They're all whole numbers. So we round to 1 decimal place. So our mean would be a 22.8. 7 rounds this other 7 up. And our standard deviation would be a 10.4. Really neat, huh? Now, here we have a little arrow telling us that there's more to see. And oh boy, we have more to see. Here we have the 5-number summary, which includes the median. So it's part of the package. So this is all the stuff that we needed to find. We're just missing 2 things. The variance and, well, the box plot, obviously. The quickest way to find the variance, my professor taught me this. It was really cool. Once we do one_var_stats, this will reside in the calculator's kind of memory, RAM if you want. So we go back to the main calculator window. Now if we go over to vars, this key right here, and we choose option 5, which is statistics, and then we go down to number 3, which is Sx, the sample standard deviation. And then if we press the squared key right over here, that's gonna square the standard deviation, thus giving us our variance. Pretty neat, huh? And the very last thing that we need to do is to construct a box plot. So, to do that, we'll go to second stat plot. We're gonna go ahead and activate plot 1. Now we're gonna choose a modified box plot. So there are 2 box plots. This one's the regular one. This one is the modified one because it's got the little dots for outliers. So let's see if we actually have any outliers in this data set. Xlist is list 1, that's where our data is located. Frequency, we just won't worry about it. We'll leave it as a 1. And for mark, you can choose what little mark to have for your outliers. The square here, the very first one, is the most visible, so I'll just leave it as a square. And then to see our actual box plot, we go to the zoom key, and then we'll choose option 9, which is zoom stat. And bam! There is our box plot. Isn't she beautiful? You hit the trace key, you will be able to see the 5-number summary. Got a 2, 16, 22, 30, and 44. And it seems that there were no outliers, hence why there are no little squares. So if there were, the calculator would have shown them right there. And that's how we find all of those values using the TI-84 calculator. How about we take a look at how to find it using StatDisk? Let's go. Now on StatDisk, this time it will be able to help us with this problem. I was able to find how to do this, and it's pretty neat. You're gonna like this. Now to find all the cool stuff that we need, let's go over to data, and then we'll go over here. Explore data, descriptive statistics. So now we choose the column where we have our data in. We hit evaluate. And look at all this stuff. Yes. We got mean, median, mid-range. I don't even know what this is. We got the variance, standard deviation, coefficient of variance, that thing that we're probably not going to see, the 5-number summary, and then this is like chapter 9 stuff. Chapter 7. It's way in the future. And over more to the right, we have a histogram. And more importantly, we got a box plot right there. Look at that. It's got the 5-number summary. So yes, isn't that awesome? Indeed it is. So the descriptive statistics here will give us everything that we need. So it's a really good, really good tool. So thank you StatDisk for cooperating this time. Unlike the previous 2 times, I forgive you. But yeah, this is how you do this on StatDisk. Hopefully it'll be able to help you out. So that about wraps it up for this video. We already compared and did a whole bunch of stuff with the means and the standard deviations and all that jazz. Now, the next video, we're gonna throw all of the stuff we just did out the window. Don't you just love it when you get used to a certain topic and then you just set it aside and do something completely different? That's exactly what we're gonna do. We'll be working with probability in the next video. Got some basic probability concepts, some basic probability rules, and also counting. If you thought you knew how to count, think again. Probability and other stat stuff is gonna tell us otherwise. But yes, thank you for your attention, and I'll be seeing you next time. Bye.